Our standard cosmological timeline starts with a single event, 13.8 billion years ago. We can see that history etched into the light of the Big Bang itself. Within this timeline, nature enforces a strict speed limit. Information and light travel at a constant 300,000 kilometers per second. Nothing moves faster. If light has been traveling for 13.8 billion years, math suggests a maximum size. A sphere with a 13.8 billion year radius has a total diameter of 27.6 billion light-years. But astrophysicists measure the actual observable universe at a diameter of roughly 93 billion light-years. This creates a direct contradiction. The universe we see is physically wider than light has had time to travel. This discrepancy exists because no physical object actually broke the cosmic speed limit. To explain the gap, we have to look at the behavior of space itself. Space is not a static backdrop. It possesses a scale factor, a mathematical property that allows the vacuum between galaxies to actively stretch over time. This grid shows the mechanics at play. The oldest light we detect today left its source 13.8 billion years ago, but it had to cross a medium that was expanding as the photon traveled. While the light moves forward, the expansion of space carries the original source in the opposite direction. By the time that light finally reaches Earth, its origin point has been pushed to 46.5 billion light-years. Since this expansion happens in every direction, we end up at the center of a massive bubble. That 93 billion light-year diameter is a direct record of how much the universe has stretched. This shifts our perspective of the cosmos from a physical container to a specific point of view. We define the observable universe as a causal bubble, the maximum distance from which light has had enough time to reach human telescopes. This bubble is relative to the observer. If we were on a galaxy 10 billion light-years away, our observable horizon would shift, encompassing an entirely different volume of space that is currently invisible to us here on Earth. Because the universe has no center, the edge we see is merely a limitation of physics. Space continues far beyond our current line of sight. The stretching of space is currently accelerating. At vast distances, the cumulative expansion between us and the furthest galaxies is now increasing faster than the speed of light. This acceleration creates a one-way threshold. Galaxies are constantly crossing over this cosmological horizon, where they vanish from our view and become unreachable. This region is the unobservable universe. It is permanently disconnected from our reality. No light or signal emitted from these distant zones will ever cross the expanding gap to reach our telescopes. From our specific vantage point, the volume of space containing accessible information is actively shrinking as more of the cosmos recedes beyond our reach. If we can't see most of the universe, we have to find a way to measure the size of a structure that is physically hidden from us. To do this, astrophysicists use spatial curvature. By examining the geometry of the light inside our local bubble, they can calculate the likely shape and scale of the entire cosmic structure. Current data from missions like Planck show that our local observable space is almost perfectly flat, with a 0.4% margin of error. This suggests we are standing on a microscopic patch of a global geometry so vast its curvature is nearly undetectable. Statistical models based on that flatness suggest the true universe is at least 250 times larger than our observable bubble. That would put the total size at roughly 11.6 trillion light-years across. If we account for the rapid expansion of the early Big Bang, that number could be 10 to the 23rd power times larger. In many models where the curvature is exactly zero, the universe is physically infinite. This 93 billion light-year span is a finite, isolated droplet within a cosmic expanse that likely continues forever.